Hi everybody, and welcome back to Digital VLSI Design. I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 9, Routing. So in today's shorter Kahoot, we'll only have 7 questions. The first is, what are the objectives of the routing process? To connect all the nets to their pins defined in the net list, to ensure that no DRC violations are created on routing layers, to meet design timing constraints including signal integrity, or all of the above. Well, I think it's going to be all of the above. So let's go back and see where we discussed this in the lecture itself. We said that the problem with routing is that we have millions of wires in the design. Not only do we have to connect all the pins on all the hundreds of thousands or millions of standard cells to each other, but these wires are actually made up of many of these polygons that are in different metal layers connected by vias. This is a huge problem that we have to deal with. We must connect them all. That's the whole thing. We have to take our net list that shows all of our cells that are gates that make up our design and their connectivity to nets, and we have to make sure that all of them are connected in the layout with actual polygons that are shorted together. Okay, so this is very complex from a geometric standpoint. So what we do is we take a grid representation, which will simplify things, and then we have to go over and incrementally fix the DRC rules that happen. But what we showed during the lecture is the standard approaches for doing these things with maze routing, and we didn't discuss maybe the detailed route type of fixing the DRCs, but that's just an incremental thing that runs on top of these basic algorithms. It gets pretty complex at nanoscaled technologies where you have hundreds, maybe thousands, very complex DRC rules, but that's something that can be done and if you use your imagination by starting with what we discussed in the lecture. So it's not enough just to connect the wires. We have to also make sure that we meet our timing constraints, and we have to also make sure that we don't have noise between the signals. So we have to deal with a bunch of things. Connection of all the wires, make sure that we meet all the design rules, make sure that we meet timing, and make sure we don't have too much noise above what we wanted. In fact, that will actually go back into the timing usually. So going back to the Kahoot question, to connect all the nets to their pins defined in the net list, obviously that's the must do. We have to make sure that our design is connected fully so we can pass LVS later on. To ensure that no DRC violations are created on routing layers, again, we're not allowed to fabricate things that have design rule violations, so this is something that we have to do with the router. To meet timing constraints, including signal integrity, again, what we need to do in our design always is to meet max and min delay and the other timing constraints and DRVs that we discussed. And indeed, signal integrity, which is noise, we have to make sure we meet the signal integrity definitions that we put for ourselves. So question number 2, choose the correct order of the maze Lie routing approach. Let's see, we have cleanup, choose a net, expand, and backtrace. I think we'll start with choosing a net. Then we'll expand, backtrace, and cleanup. That looks a good one. So let's look at maze routers, or also known as Lie routers, based on this seminal paper by C.Y. Lie. So the thing is, what we have to do is we have to choose a net. This is actually a heuristic or one of our decisions that makes our solution suboptimal. We have to choose which net we do first. We have millions of nets, or thousands or millions or whatever, and we have to really choose one of them, and it can do all kinds of things like the blocking that was shown in this little schematic over here. Okay, but once we chose a net, what we're going to do is use this maze routing approach to find the best wiring for the current net. And the way we do it is we first of all expand, then we backtrace, and then we clean up. And that we'll see in the next Kahoot question. So question number 3, what is the cost of routing to the final target in the multi-target net shown in the picture? So this is a hard one. Well, let's see. We have the source over here, and let's say we start with 1 here, then it'll expand 2, then it'll expand, say, 3, then it'll expand, say, 4. Okay, we get to the first target, and then we would mark this whole thing, as a net. Then saying we start for the closest over here, that would be 1, 2, 3, 4, 5. So I'm going to say 5. Okay, let's see that in action again as we saw in the lecture. So actually what I tried to show you in the lecture is that taking our maze routing, we can not only deal with, finding the shortest path between a source and a target, but we can deal with some other features that we have of nets in an electrical design, such as the fact that we have a multi-point net, such as the fact that we have preferred routing directions, such as the fact that we have vias, and different wires will have different costs, etc. So I just wanted to go over one of them in the Kahoot, but you should really look at the other ones in the lecture and understand how they work. So how do we do it? It's pretty straightforward. Okay, we start with our regular maze routing to find the path to the nearest target. So we start with a 1 on the source. And remember, this is just an electrical wire. It's an equipotential wire. We don't care what we mark as the source and the target. It doesn't have to be from the output of a gate to the inputs of a gate. We could do it from any one of the pins on the gate. Okay, then we go to each direction, north, south, east, and west. Again, north, south, east, and west. Remember, we're doing Manhattan routing, which means we don't have any diagonal routes. So we're only going horizontal and vertical. Okay, and look at that. We got to number 4, hit our target, and then we backtraced 4, 3, 2, 1. So that was expand. Now we did backtrace to mark our routing to the first target that we hit. Then we clean up and remove everything. And what we're going to do during cleanup is we're going to relabel all the cells that were on that as sources. Okay, so now we have our source, and this is, this whole wire that we backtraced and cleaned up is our source. Now what we're going to do is we're going to mark all of them as 1. Okay, so then we can expand again from each of these, north and south and east and west, and we'll get 2s all over the place over there, then 3s, 4s, and finally we'll hit our target, which is 5, and now we can backtrace again from 5, 4, 3, 2, 1, and we can clean up again. So the answer was indeed 5. Question number 4. What do we mean when we say XYZ metals? The preferred routing direction, horizontal, vertical, of the metal layer, the minimum width, spacing, and thickness of the metal layer, a signal that has not been routed yet and needs to be randomly selected, or metal layers fabricated in emerging processes such as with air gap interlayer dielectrics. Well, I'm going to choose the blue one, and I want to mention that I didn't discuss this very much or at least very explicitly in the lecture, but it's an important point. When you look at your standard cell library, you're going to actually get your technology left, your tech left, and it's going to say something like, 1X, 1Y, 1Z, or something like that. And what that is trying to discuss is the metal stack that we have. So we're going to have usually different options of our tech left files for different metal stacks depending on what we're actually ordering from the fab. Okay, so to understand what it is, let's go back to this this slide that we saw about layer stacks. And if we go to older technologies, such as 130 nanometers, and this is just representative, it's not from an actual technology, but what we had a bunch of metal layers, and all the metal layers were exactly the same. They were aluminum, they had the same spacing and width, minimum spacing, minimum width, the same vias that actually connected between them. The only difference maybe was the contact layer. They were really just a one single type of metal. But what was seen is as we got more layers, what we understood is that we need to actually deliver power really efficiently and robustly to the whole design. To deliver power better, we want less resistance. For less resistance, we want higher metals, and that's not really good for routing signals. So what the decision was to do is to take the highest metal layers and use them for routing strong signals such as power, maybe clock. And so what we did is we made a much higher layer. We have much larger minimum widths and minimum spacing between them, but these are not used for fine signal routing, just for top layers. And in this case, we have 2 types of layers: the lower layers, which have the height of lithography with minimum width and minimum spacing that we could get into our design rules, and at the higher layers we have something much bigger. The vias are much bigger, etc., so we can deliver more current and have less resistance. it got even better than that. We started to have usually three types of layers. So the lower layers would be for, a local interconnect to connect between gates and really close by things. Then we go to a global interconnect type of a layer where we would be connecting things that are farther away, and therefore we don't want the wire to affect their delay as much. And so we would be able to go up through vias up to one of these top layers and go farther in the chip. For example, clocks usually will be try to be in these types of layers. And then we would have these top layers that are really for almost exclusively for power and maybe for some of the trunks of the clock tree. It can even get more than that. We can have 4 types of layers and more, and the top layers become really, really thick. So what we do is we usually call, if we have 3 types of layers, we'll call these bottom layers with minimum rules. We'll call them X layers, these Y layers, and these Z layers. Now, you should know that nowadays we have many differences. We have double routing and double patterning and quadruple patterning on the lower layers. And so you will have different types of names in these types of layers. You also have colors of these guys, but I'm not going into that in this course. So it gets more complex than just X, Y, and Z, but they will be also called with some sort of name. And obviously, when you get your technology PDK and so forth, you should look and understand what the different naming conventions are and what types of backend layers you have. Now, I just want to mention one more thing. If we look at our tech left, we were going to have several options of routing layers, because as a company or as an academia, when we're ordering a tape out, we can ask for different metal stacks. However, usually, in most cases, the standard cell libraries will only come with one metal stack. We won't have different options for standard cell libraries, which is also kind of important because the standard cell libraries, especially with the libs, can get become very big deliveries. And the reason that we can do that is, as we remember, standard cell libraries, we try to make them only with metal 1 inside. In fact, it could be that in newer processes, we might have only what they call metal 0 inside. So as long as we don't go up past the initial layer, the X layer, that means that if all of the flavors of the backend flows will have at least one of these X layers, we don't need to differentiate between what the higher layers on top of them are, and then we can provide one lef for our standard cell library and one lib, etc., regardless of what the higher metal stacks are. So really, that was the answer to our Kahoot. The other ones were just wrong answers. Question number 5. Which of the following is not an objective of global routing? Balancing congestion, fixing DRCs, meeting timing constraints, or minimizing wire length? Well, I believe the answer is fixing DRCs. And let's go and see why. So, what is global routing? In most of the algorithms that we went over in this course, we divided them into 2 stages, a rough stage and a fine-tuned stage. And that's the same thing that we do here with routing. So routing is a huge problem. As we said, we have to deal with millions of wires. They're very complex, especially when we have to go and take into consideration all of these very complex DRCs that we have in modern technologies. So what we're really going to do is we're going to try and divide this into at least 2 stages, where the first stage, which would be global routing, is going to really break our design into much more rough detailed parts. We call them G boxes or global boxes, and you see that one of these boxes will have something like 10 tracks per layer on each side. That will be a G box. And then when we run our maze routing algorithm, what we're going to do is we're not going to say that once we used a certain G box over here that it is blocked, but maybe that it has some sort of a larger number of options. So only when say we have 10 tracks over going through this edge, if we use it once, we'll reduce that to 9 tracks. We used it again, we'll reduce it to 8 tracks, and so forth. And this also enables us to balance congestion. So we will try to have the fact that in each of these lines that crosses through G boxes, we're going to really have them get to a situation where they don't have congestion, and the congestion is balanced through the design. So once we select the G boxes for a route, so say we took a signal and we wanted to route from somewhere somewhere around here to somewhere around here. We had a standard cell over here and a standard cell over here. We're going to mark, we decided with our maze router to mark this as the track that our net is going to take. And that's fine. Now we can go and look, after we did it for all of the nets, you know, that we have inside this box, we can go and look only at this box. And that's a much more bounded problem. It's a much simpler and smaller problem. We have much fewer, we have many fewer nets to actually detail route, and then we can go and route them in a detailed fashion using the source. Well, if we take one of these boxes, for instance, this is in the middle of this net, we would say where it crosses over into the box, that's going to be the source, and where it goes out of the box is going to be the target. And now we just have to maze route with detailed route and fixing DRCs inside this G box. And in the end, we'll connect them all together, and we'll get the actual detailed route of our long net. So what is this helping us do? First of all, minimizing wire length. That's the cost function of all of our maze routing. So this is going to give whatever type of a weight we have for each type of movement, if it's up, down, left, right, vias, etc., as we discussed through maze routing. And this is actually a part of another non-optimal part of our algorithm, of our approach, because these weights, what do they mean actually? And in this case, we're using wire length as our only cost target in this case, and we hope that it actually is proportional to what we want to optimize in our design. The second thing is we're going to try to balance congestion. So if we see that we already filled up all the tracks, going from the top to the bottom, then we're going to detour around to get over here or something like that. Okay, it's timing driven because now we can actually know what we expect to be the real length of this wire. And if we know the length of this wire, we can give a good estimate of what the RC on the wire is, and we can put it back into our timing equations, our timing constraints, and we can see how we're doing in a timing wise fashion. It can also look at noise in SI because it knows if we have some critical nets that we can probably make them farther away from each other or give them a higher cost to run away from each other, and we can try to keep buses together. So those are kind of the objectives or the goals of global routing. Once we do that, we can take it and we can actually assign each of the nets inside to a track, and then run the detailed routing and fix our DRCs, etc. in the detailed route stage. So balancing congestion is for sure one of the objectives of global routing. Meeting timing constraints is a goal of timing-driven routing, which is something that we usually apply. And minimizing wire length, that's the main cost function of this whole algorithm. Fixing DRCs, however, is relegated to the detailed route stage. Question number 6. Which of the following approaches is not a solution for signal integrity SI violations? Downsizing the victim driver, increasing wire spacing, adding shielding, or limiting length of parallel nets. Well, these actually all look to me like solutions for signal integrity violations. Actually, it's not downsizing the victim driver. We want to upsize the victim driver, so it must be this one. So let's look at signal integrity. So when we discussed signal integrity, I said that signal integrity is a name that's synonymous to crosstalk. So when we discuss signal integrity, when we're talking about routing, it means that we have some sort of coupling capacitance between two wires. And when we make a transition on one wire, it's going to cause a cross-coupled transitional glitch type of an effect on another wire due to the capacitance that we have in between these two wires. Okay, so what we do is we call the switching net, we call it the aggressor, and we call the net that is affected by it but isn't supposed to switch, at least not due to that toggling, we call that the victim. Okay, and this can either cause speed up or slow down. So if we had at the same time both the aggressor and the victim transitioning into the same direction, the transition here is actually going to push it down, and it's going to help the operation. And if we help the operation, we're going to get a speed up in the transition through the victim net. If they're in opposite directions, we're going to, this started to transition down, then the transition over here came, the coupling capacitance drove it up, and we have to again, discharge this whole net. So it's going to cause a delay in the transition of the victim net. Obviously, speed up, if it's on a data path, it's going to cause hold violations or make meeting hold constraint harder, and delay is going to make meeting max delay harder. Okay, so setup violations. So both of these options are available. And so what do we do to solve them? First of all, the coupling capacitance is a function of the distance between the wires and the mutual like overlapped area. So the best way to do it is just spread them away from each other. If we move the victim wire away or move the aggressor wire away, if we can put that into our global or our detailed route, into considerations, then we can really reduce the crosstalk between these two nets. Obviously, congestion is a problem, because if we have congestion, we're going to have mini nets next to each other. That's number one. Number two, we can upsize the victim driver. So the stronger this driver is, the less the effect of the coupling will be, and then it will make this speed up or slow down a smaller effect, and we hopefully will still meet our timing constraint. If, on the other hand, this is a really, really weak driver, nothing's going to hold this, and we're going to have a real big glitch on the victim. So those are two options. Obviously, if we're running right parallel to each other, we can change metals or something like that, and then they won't be the overlap between the two of them will be smaller, reducing the crosstalk. And another thing is that we can shield, either route a different net in between them, one that isn't critical or isn't going to be so affected by the aggressor's transition, or actually put a real shield here, such as we did in clock net routing. So those are the real approaches for solving crosstalk. But I also want to tell you that up until around 130 or 90 nanometers, what we used to do is we used to use this approach called the infinite timing window analysis, which meant that we would take the cross coupling, we would take the transition on the net, and we would assume that at any point in time we could have this transition, and at any point of time we could have this transition, and so we apply like a worst case effect over here. The problem is it caused us to have to add way too much margin. So remember our delta margin in our timing equations. Well, one of the things is actually the extra margins due to possible crosstalk type of effects, and it was becoming too big, and we weren't able to optimize our designs enough and so forth, when it was clear that sometimes we're adding margin that can actually happen. And that's when Synopsys introduced a tool called Primetime SI, which introduced this thing called propagated window analysis. So if we look at these two signals, this is the aggressor maybe, and this is the victim or something like that. What we do is we can look at the minimum delay of the falling transition, and we see it happened over here, and the maximum delay of the falling transition is over here. So the window that this signal will transition is only between this time point and this time point. It will not transition anywhere over here or anywhere over here. So then we look at the other net, and we look when it's going to transition, and we see that it will transition over from this point until this point. So the overlap between them is actually only in between here and here. So only at this point, if there is such an overlap, should we add this worst case timing. If these two things do not overlap, we'll only have the single transition and not the double effect of the noise. And that is a harder thing to consider. As you can see here, we had the crosstalk here. If we had two nets in this case, like that, we're both transitioning. If, for example, our victim was in between two aggressors or something like that, we would actually have to add the noise from the first one and the noise from the second one according to our propagated analysis, because both of them were overlapping over here, and they would cause a worst case combination of the two, and that all goes into our timing equation. So again, increasing wire spacing is the standard approach. That's what the routers will do. They will do some SI analysis during timing optimization during the routing process, and they will try to increase spacing where they see they have high SI type effects. Adding shielding, well, that's kind of a more extreme way to do it if you have a really critical net or something like that. Again, we do it on clock nets, maybe on analog nets and so forth, but it can be done by the router by just sticking a different signal in between. And limiting length of parallel nets, I mean, that's a pretty also easy one. A certain net that has a lot of crosstalk with another can just change, and jump up to a different metal layer or something like that, and reduce, the coupling between them or something like that. And the final question for this Kahoot: which of the following is not a DFM or DFY recommendation? So just as a reminder, DFM is designed for manufacturing and DFY is designed for yield. So via minimization, adding redundant vias, providing 30 to 70% density within a metal layer, or wire straightening and spreading. Well, these two look like they're opposite to each other, right? And this, well, we discussed that for sure. But, wait a second, this is a DRC, so it must be that this one isn't the DFM or DFY recommendation. And indeed, that was the answer. So let's go back to what we discussed about DFM and DFY. So design for manufacturing is additional type of DRC rules or type of optimizations that we try to apply, not because they're actual DRCs and the fab has said that, listen, this is not going to work and we're going to get really bad yield, but if you follow these rules, there's a better chance of getting higher yield, and that's what DFM or DFY are. In your DRC rule deck, they will be called recommended rules. So sometimes like a .r rule or something like that, and you might disregard them or you might take them into effect, but it's better to take them into effect, and your router will actually have options to do incremental iterations to go and fix these things. So as I said, there's kind of a contrast between these 2 points, via reduction versus redundant via insertion, but they actually mean something completely different. So the problem is that vias are these small things. They're these chimneys that are really thin. They have higher current density, so they're susceptible to electromigration. They're not easy to manufacture, so there's a higher chance that one of them won't be manufactured well, either causing an open or higher resistance through it. So if we can get rid of vias as much as possible, that's really good. So if we can stay within the same metal layer and not go up and down through a via stack, that's something that we want to do. And really, we can look at our final solution of our route and see if there are options to go and take vias and get rid of them. On the other hand, if we do have a via, then we want to have as many vias as possible. We want to have an array or something of vias or a vector of vias. So as you can see here, we have this area that needs to go down to this to this metal over here, or to this metal up here. Sorry, this one needs to go down to this one. So instead of just putting one via, we'll put a whole bunch of vias. First of all, that will mean that if one of them is no good, the other ones will take its place, and we won't get a short over here. Same with if we have an electromigration problem, one of them blows out, we'll still have other ones to take its place. And second of all, it reduces the overall resistance and current density for electromigration problems that we'll have through these vias. So really, if we can, we want to put as many vias as possible across the design. In many of the rules, you'll go over your design and see how many single vias there are versus double vias, and you'll want to have a very high percentage. It could be even 90 or 95%. You want to have double vias across your router design. Okay, wire straightening. So this whole maze routing thing is an iterative process, especially fixing DRCs and stuff. Things are ripped up and rerouted, and we often get weird types of routes that you can't understand why the tool did it. It has these weird things, like in this case, we have this weird jog over here, and there's no reason for it. So if we go and look at it again, with a clean eye, and we say, whoa, there's no reason to do that, we can just straighten this, and that really improves everything. I mean, it improves our RC of the net, but it also improves the problems of yield where these types of bends are not healthy because they can be missed with all kinds of misalignment and so forth. So just straightening this thing is a real improvement, and there are lots of these options that occur after routing millions of wires. Okay, so that's wire straightening. Wire spreading is another thing that if we have a defect, the higher the density of the wires in a certain area, the higher the possibility that it will actually break our design. So if we have extra space, we can spread the wires. It's also better for crosstalk and so forth. And then if that particle hit where my mouse is right now, then basically nothing's going to happen to the design. I mean, particle, during manufacturing, then it's not going to ruin our design. Versus if it would hit anywhere in this whole area, then our design would probably be ruined. Okay, so that's what design for manufacturing is. So going back to our Kahoot, we said that both via minimization and adding redundant vias are two DFM recommendations. Wire straightening and spreading are also recommendations, but providing 30 to 70% density within a metal layer, that's what we call density rules. That's not a recommendation. That's a requirement. We have to do that. It's a regular DRC. We have to use metal fill or whatever to meet density rules. So that's not a DFM. That's a real DRC. So that's it for this week's Kahoot, and you can, as usual, ask me questions on my YouTube channel and find the Kahoot and practice it yourself with the link in the notes. Okay, thank you everybody.